So good morning. So first of all, many thanks to the organizers for inviting me. It's a great honor to be here. I owe actually my career, the very fact that I stayed in physics to Abdus Salam. And in the first part of my talk, I will discuss this, and we'll also add, the role of Salam from a different perspective, which has not been discussed here so much, namely from the point of view of Pakistan as a developing country in a crucial period of its development, in which Salam played, of course, a central role. And I would like to elaborate this, because partly I was a witness, and partly I also benefited from that. So the second part of my talk is, if you wish, is a scientific homage to the standard model that means the electroweak theory of Salam, Weinberg, and Glashow. And we have heard about it from Peter Yanni and Jim Verdi. Standard model is being tested at the forefront of the energy at the LHC. And so that's one frontier of high energy physics. The other frontier is high luminosity. That means you probe rare processes, and due to the fact that in loops, in virtual corrections, all kinds of particles which are present in nature can, in principle, contribute. And therefore, the study of rare processes is both. It is a quantum study of the standard model at the quantum level in processes which are not allowed in the Lagrangian, but are only possible through loops. And by the same token, then it is sensitive to physics beyond the standard model. And so the question is, that frontier is also being studied with great dedication. Also at the LHC, there is a dedicated experiment, LHC-B, but also at the B factories, at KEK, at SLAC. And therefore, I would like to add the scientific aspect here, which I thought did not come out so clearly. Okay, so, but let me turn to the first part. So when I I can't say I met Salam, I saw Salam. And so it was in 1964. I was an undergraduate student in the physics department at Karachi University. And there was a science conference in Karachi. At that time, he was scientific advisor to the president of Pakistan, and very graciously agreed to come to the Karachi University physics department and give an inspiring lecture. Now, at that time, it was late 1964, probably December. He looked something like this to me. This is my early memories of Abdus Salam, a very dynamic person. And so this lecture, as most of his students and collaborators would also testify, was a very lucid lecture, very inspiring. But at that time, he was working with John Ward. Actually, in October of that year, he had written this paper, which was, the first serious attempt in electroweak symmetry breaking, electroweak symmetry unification. And so he talked about it. Now you can imagine very well from the perspective, and in particular from the level of knowledge of an undergraduate, it was a little bit too difficult to follow, but he was a very lucid lecturer, and after the lecture, we left as if we understood everything. So this was my first impression of him, and in fact, at that point, it was not clear to me what I would do in my career. Because if you are coming from a developing country where the opportunities are not so well defined and are not there, then you don't know which way. I mean, even if you are a student of physics, you don't know where you will end. So at that point, for me, it was rather inspirational. I decided that I would try to follow him. So that was a very important occasion that he came. The second time I met him was again, it was December, a year later, 1965. And the occasion was that and I will talk a little bit about the next picture. This was the occasion. This is the Pakistan Institute of Nuclear Science and Technology, which was set up near Nilore, at Nilore, near Islamabad. So this is a 5 megawatt research reactor. And so we were sent to see this reactor, being a student of physics and other centers of physics and other departments of physics. So that was the main goal of our trip. So I will talk about it a little, but let me. So at that time, Salam was the presidential advisor, scientific advisor. And you see in this picture, we met him at the Atomic Energy Center in Lahore in 1965. Now I don't know, but perhaps Professor Munir Rashid might have been working there at that time. And I mean, these you see a few people here. So this is Salam. Now this also is a very, very important person in the context of Pakistan nuclear science. And his name is Ishrat Hussain Usmani, Dr. I.H. Usmani. He was the chairman of the Pakistan Atomic Energy Commission. And this gentleman here, his name is Dr. Shaukat. He was the director of the Atomic Energy Center in Lahore. Now, these two gentlemen here, Salam and Usmani, I mean, the history of Pakistan Atomic Energy Commission is that it started in 1955, but it was a bureaucratic organization, and nothing much was going on there. And when Salam became the scientific advisor in 1960, this was the time of General Ayub Khan in Pakistan. It's called the period. He was the president from 1958 to 1969. So there is a decade, 1958 to 68, which was celebrated later. It is called the decade of development. Now, of course, he was a military general. He overthrew a constitutional government, and he came to power, and there were a lot of people who were unhappy with him. And I was quite active in my student days in student politics. I was also against him. In fact, I demonstrated with a left-leaning political party, and I was arrested and put in jail. So nevertheless, I mean, things change. And I would say, despite all of this, and I compare his period with what followed, I have to revise my opinion. I agree, it was a decade of development. And in particular, what concerned education, higher education, there were many universities which were opened in what is now Bangladesh, at that time East Pakistan, and in Pakistan. And there was a rapid development in science and technology. Now, these two gentlemen, so on the recommendation of Salam, Ayub Khan appointed Usmani as the chairman of the Atomic Energy Commission. And the two of them actually put essentially Pakistan onto the nuclear map. So this pin stack has played a very important role in the nuclear ambitions of Pakistan, both peaceful and otherwise. Now, the very fact there's been about a year ago a very impressive article in Physics Today, which appeared with the title "The Nuclear Taj Mahal of Pakistan." And in fact, when I visited this, it was very impressive. It's a very, I don't know how it is now, but at the time it was a very impressive building. And so Salam and Usmani were principally responsible for the establishment of this. And I should say that, Salam was Salam's role in that was very, very important. Now I have to go back a little bit and say that in 1953, the President of the United States, Eisenhower, made a speech in Geneva and later in the United Nations, which is called Atoms for Peace speech, in which he offered in some vague sense is what Mr. Obama is also doing now. He offered the transfer of American nuclear know-how and for peaceful purposes, for generating energy, for medicine, for agriculture, and other peaceful purposes. And therefore, in 1955, I was reading some of the books. An agreement was signed between Pakistan and the United States government for such a peaceful nuclear collaboration. But it was lying idle. I mean, there was nothing. There are lots of these memoranda of understandings which are signed. I mean, and who cares? I mean, they just are shelved. I mean, and they are only important for historical reasons. And Salam and Usmani invoked that. And in fact, Salam went to see Glenn Seaborg, who was the chairman of the what was called at that time the American Atomic Energy Commission. And he convinced him that that there is a need for this in Pakistan, and this was actually what convinced Glenn Seaborg, and as perhaps to motivate them, he even offered that they would pay them $300,000 US if they are able to show that it works. So that is what happened. It worked. And so the occasion was this reactor became critical on 23rd December 1965. Salam had come at that occasion to Pinstek and to Lahore, and that's how we met him. But his role is rather important. At the same time, let me go to this picture, which is also very important in the context of Pakistan, also explains a little bit about Salam's role in all of this. I mean, just like Norman Dombe's article, which is half the truth. I should say I was very annoyed reading it. And previously, I don't know, but I think people who worked with Salam in the 1960s and later also 70s knew that he could at times be very impolite and brash. And I suppose, without any, trying to overinterpret his articles, that there must have been some personal reason which prompted Dombe to write that article. Anyway, so also about Salam's role in the Pakistan nuclear bombs is very often misstated in the literature, and there are some articles. I think it is a tendency among some of us when we grow old, when we are retired, then we make forays into histories. We are not trained historians. We don't follow the rules. We don't really, go into the details what a professional historian will do. And very often these are opinions which are expressed in the name of facts. So this picture in the context of Pakistan is very important. So we are now in 1972. Pakistan lost the war against India, and East Pakistan was lost. It became independent. Mr. Bhutto became the president of Pakistan. And the first thing he did, imagine, in December 1971, the war was over. He became president. And in just within 2 months, in 1972, he calls a conference in Multan. And there he made this famous statement that we will make the bomb even if Pakistan has to eat grass. So I would venture to correct it a little bit. What he really meant was if Pakistanis had to eat the grass, not he himself. So he called, now this is 1972, and the gentleman that you see in the middle, he is a very important person in the context of Pakistan. He was a personal friend of Abdul Salam. His name is Munir Ahmed Khan. And Munir Ahmed Khan, in this meeting, Salam, it was a select meeting. He only invited those about whom he was advised that these are the people who are physicists and engineers who are working either with the Atomic Energy Commission or have the expertise. So it was a very select meeting. And he just asked them how long will it take and what will it take and so on. Now, quite frankly, and this is recorded actually in many, many books, neither Salam nor Usmani were actually very much in favor of this. So Usmani, he was a civil servant. He had a PhD in physics from Imperial College, and that's how Salam knew him. But he joined the Pakistan Civil Service. And before becoming the chairman of the Atomic Energy Commission, he was the chairman of the Import-Export Corporation of Pakistan. So he built the atomic energy from an administrator point of view. He knew, the problems, he knew the challenges, he knew the capabilities, and he told Bhutto that it is not a very workable program. Mr. Usmani was removed in the same meeting, and he was replaced by Munir Ahmed Khan, who at that time was the head of the power division of the International Atomic Energy Agency in Vienna. So he was called and he was given this task, and he was the chairman of the Pakistan Atomic Energy Commission for 19 years, from 1972 to 1991. And it is he who is really the one. You see also Salam here, greeting Bhutto and so on. But actually, this meeting marked the end of the Salam-Usmani duo, of Salam-Usmani collaboration. And Salam being a very, very sharp person, he actually had already read the readings on the wall. This was the beginning of the end of his collaboration, his role as a scientific advisor. And so in 1972, I was at ICTP, and he returned. And I should say before that Salam helped me. In 1968, he was awarded the Atoms for Peace Prize, and the money that he got, he put in a bank, Casa di Risparmio di Trieste, and he had a fund. So Salam's Atoms for Peace Prize, and I was one of the recipients of that fellowship. I came with that fellowship for 6 months because it was very difficult after the war to get anything, no job, nothing. So that was rather crucial. And so Salam actually returned to physics, and if you look at his papers from 1972 to 1974 was another period of intense scientific activity. He was collaborating very intensely with Jogesh Pati on the possibility of proton decay on SU4. And in fact, I attended the 1973 Aix-en-Provence conference in which the discovery of the neutral currents from the Gargamel experiment was announced. And I attended that meeting. In that meeting, Weinberg gave the plenary talk about what we call today electroweak physics. And T.D. Lee was the chairman of the session. And as a courtesy, T.D. invited Salam to make some comments. and remarks about this. And for Salam, electroweak unification was a done deal at that time. So his mind was somewhere else. He was working on SG4. He was working on the next unification. And he talked about his work with Patti. He completely ignored what was said by the experimentalists, by Gargamel, what was the purpose of the remarks by T.D. Lee. And he said that, I'm very sorry, but I would like to tell you about this new work that I'm doing, and I'm very excited about this. And you can read also other papers that he, so he actually, in his mind, he had disconnected himself. In 1974, there was a legislation passed in Pakistan in which he and his sect was declared non-Muslim. And this thing can only happen in a country like Pakistan. And at that time, it was a total break. But I think from now on, he had nothing to do with any of these things. He was no longer any advisor. He was not involved. But of course, he remained committed to Pakistan. He remained committed to the physics community, to many of us, he was coming, giving lectures, Natia Ali College, and so on and so forth. But all his association with the government, with the atomic energy, and all of that ended in 1974. So, I mean, so whenever they talk about his role, whatever, I mean, there are many such articles, mostly nonsensical, not well researched. He had nothing to do with this. Now, so anyway, so this is my, I should also say, another very important person in the Pakistani context. So this is Salam's student, probably his first student could be. He is Riazuddin, who is known from his work which he did on, KR-SF relation. So this R stands for Riazuddin. So he actually played a very important role in establishing the theoretical physics within Pakistan, and I am also a student. He's a student. And finally, I ended up together with Chris Isham and Tom Kibble and Riazuddin to compile the collected works of Abdul Salam. This happened quite late, and this was published by World Scientific. So this is, so for me, he was a role model. For me, he benefited, he helped me at a very crucial moment in time. And I'm very grateful to him for this, because without his help and without his personal, fellowship which he gave me from his fund, I would not have been able to come back. Now, I've talked a lot about this, so let me be very quick and talk a little bit about the scientific aspect. And this is a test of the standard model in rare BTKs. So these are a few processes which I will talk about, and some of them I was involved myself in theoretical calculations. So this goes, this is a process in which a B meson goes into hadrons with an overall strangeness quantum number and radiating photon. Now B quark, in terms of the quark model or quark model language, a B quark turns into an S quark. So they have the same charge, but they are different flavors. So these are flavor changing neutral current processes. They are not allowed in the standard model at the Lagrangian level, and therefore they test the standard model at the loop level. And there are then various variations on this theme. So this is a process in which this photon turns into a lepton pair, and this is an inclusive process, and these are exclusive processes in which K meson, L plus L minus is measured, or K star, or a pion. And then there are processes in which, for example, a meson which is called B sub S goes into mu plus mu minus, and its counterpart B sub D goes into mu plus mu minus. So So rare B decay is a standard candle, and the interest in rare B decay in this particular B2S gamma actually it transcends B physics. It's a very important input in all other beyond the standard model scenarios in which this is an important input to constrain the parameters. So it was first measured by Clio in @95. It was very well measured by Bell and Babar. So these are experiments at the B factories, at KEK and at SLAC. Now, in terms of theory, it took a monumentous effort because, I mean, when you are testing a standard model very precisely, you have to calculate a lot of quantum corrections to it. So this process has been calculated to what is called next to leading order in QCD corrections. So it's an effort which went on for many years, and finally it was done. And there are aspects involving non-perturbative effects. They were calculated using so-called heavy quark effective theory, and our chairman also had to do something at some stage with it. And so this is the theoretical framework. So this is, in some sense, a study of QCD. This is the SU3 part of the standard model, the role that it plays in stabilizing the predictions of the standard model processes. So this is a typical Feynman diagram which you calculate at the tree level. I mean, this is in the full. In the tree level, it does not exist, but it mainly comes from the loops, in which the highest quark in the standard model is the top quark and W boson, and similarly charm quark and W boson. These are the dominant diagrams, and then there are QCD corrections of symbolically written like this, in which you exchange a gluon between any two quark lines. Now, these diagrams generate terms which go like alpha S, the QCD coupling constant, log of MW squared over MB squared. Now, this log is a large number, and therefore this alpha S times log MW squared over MB squared actually is not a small number. And therefore, one has to sum up contributions like this, which come from the exchange of many gluons. So that means that series is slowly converging, and one has to sum up these kinds of contributions to make a definite prediction. So this is done in an effective field theory. The effective field theory is obtained by integrating out the heavy degrees of freedom, which in this case, in the standard model, means that you integrate out the W boson and the top quark. So it's an effective theory which has then only 5 quarks, and which has no W bosons and Z bosons. But the effect of this is contained in the so-called Wilson coefficients. So this is the effective theory. So this is, it involves the Fermi coupling constant. It's a weak interaction process. It involves the CKM matrix elements, the mixing matrix elements of the quark, the 3×3 Kabibo, Kobayashi, Maskawa matrix. And it involves these operators in the effective theory, which are 4 Fermi operators, and then there are 2 dipole operators involving electromagnetic field or QCD, the gluons. So usually in this counting, the first 6 are the 4 Fermi fields involving 4 quarks with different Lorentz structures, and the 7th one is attributed to the dipole operator, electromagnetic dipole operator, the 8th one to the QCD chromomagnetic dipole operator, and then there are these 2 additional semi-leptonic operators. They will be called 9 and 10, and their Wilson coefficients then will be accordingly written like this. So the information about the theory, apart from these mixing matrix and the Fermi coupling constant, they are encoded in these Wilson coefficients. So you calculate them as accurately as possible by including by calculating perturbation corrections in order alpha S and order alpha squared, and as much as you can go. And then you have the prediction of the standard model. So at the end of the day, in an experiment, these Wilson coefficients will be measured. And if you see that they are deviating from the standard model, then this is a sign that there is physics present. And these, I mean, if there is new physics, it will enter through by modifying these Wilson coefficients. So that's the name of the game. So try to evaluate them as accurately as possible in the standard model, and then measure them in experiments and try to see if the standard model agrees with them or not. And then they become important input in any beyond the standard model scenario. So that's the philosophy how such decays are tested in experiments. So they have been calculated to a very high accuracy. And these are the Wilson coefficients. What you see here, leading log, next to leading log, and next to leading log. So all of them behind this actually are several years of works which have gone into this. So they are known in the standard model. They, of course, are functions of some parameters. And these parameters are written here: the B quark mass, the top quark mass, the W boson mass, the sine squared theta W, and so on. So these are known very well. So this is how it was measured by Clio in 1995. So this is the photon energy spectrum, what you see. And this curve that you see is actually a calculation which I did with Christoph Groib. Actually, this was done in 1991. So it agreed both in the normalization and in the distribution of this photon energy spectrum. Then later, much later in 2004, this was measured very well by Bell. So if you see the difference, you see here number of events, 40 and so on, and here you see 20,000. So this is how, I mean, this is one of the very precise measurements which was done by B factory. In this case, is coming from Bell, from KEK. And in the meanwhile, this has been calculated to next to leading order, completely calculating all the various technical contributions which are very hard to get. So this is the result. So this is what the standard model predicts. So it's a rare process. That means the branching ratio is of the order of 10 to the minus 4. And this is approximately about 8% is the theoretical accuracy of the standard model. And most of this is of parametric origin. That means the parameters which determine these Wilson coefficients and the Kabibo, Kobayashi, Maskawa matrix elements are not known very precisely. They are known perhaps to within a few percent. And so this is known at the level of about 8%. In the experiment, this has been measured very well. And as you can see, the experiment compared to the standard model agrees to within 8%. So this is an excellent agreement. And it then allows to put constraints on beyond the standard model physics. So here you can write down this result here. I mean, this theoretical result you can write down in terms of the standard model contribution, which is here, and additional contributions which can come from physics beyond the standard model. And once again, they are encoded in these incremental Wilson coefficients, delta C7 and delta C8. So as you can see that from this measurement and the standard model calculation, you can see that it puts constraints on beyond the standard model. And this is a typical diagram. So this is how a 2 Higgs doublet model, I mean a model in which there is not one doublet of Higgs, but 2 doublets of Higgs. And there are charged Higgses and other neutral Higgses which are present, which then can contribute in the loops. So they then have an influence on the prediction of the branching ratio, and they are usually functions of the charge Higgs mass and a parameter which is known as tangent beta. It's the ratio of the 2 vacuum expectation values from the 2 Higgs doublets. And this is the kind of constraint that you get. So So at the end of you get a constraint on the charge Higgs, which actually is at about 500 GeV. So you see how much. Okay, thank you. So so you see that a quark or a meson which has a mass of 5 GeV, if you study its rare process, then it allows you to actually look for physics which is 2 orders of magnitude more. So this is the spirit of this. Now there are many other processes. As I said, this is known as the electroweak penguins, so in which a B quark turns into an S quark and emits a pair of leptons. And these are the diagrams, Feynman diagrams in the full theory. This one is the Feynman diagrams in the effective theory, in which again you have integrated out the heavy degrees of freedom. Now of course you have the same operators here which I was showing, and then you calculate this and then you measure it. So this has also been calculated to the same accuracy as B to S gamma. In this case you can measure it more accurately in the sense that you measure the dilepton invariant mass. And these various points that you see, actually, they come from various experiments. And these bands are where perturbation theory cannot be used, because these are resonating areas of this Q squared, in which particles like J of psi and psi prime and psi double prime, etc., they contribute, so leave them out. But the rest of it is in very good agreement. And this is one of this, another variable which has received a lot of interest. It is called the forward-backward asymmetry. And what it does is that it allows you to put constraints on the Wilson coefficients. And as you can see, this agrees with the standard model distribution agrees with the standard, agrees with the experiment. Now this can be studied more precisely in exclusive processes, B to K L plus L minus, or B to K star L plus L minus. And here the theoretical challenge is to calculate the form factors which are present in these transitions. So these form factors is where the QCD technology is needed. So they are calculated by using various QCD calculational techniques, of which the lattice QCD is at the forefront. Now it's used normally to calculate these form factors. So the perturbative part comes in terms of the Wilson coefficients. The non-perturbative part comes in terms of these form factors. They have been calculated. So let me, and of course you can not only measure the rates for these processes, but you can measure many distributions. So you can look at this decay, in which you can study the complete angular distribution, which is written in terms of various measurable quantities. They go by these names of S4, S5, S6, S7, etc., forward-backward asymmetry, and so forth. These can be extracted from the experiment because they have characteristic angular dependencies, and so they have been measured. So this is a measurement of many of these angular variables in this B to K star mu plus mu minus, which has been measured quite accurately by the LHCb. And you see here, all these violet bands are the standard model calculations, and the others are the data points. So they have been calculated and measured very accurately. And you see that more or less the standard model is in good agreement with them. There are yet other such measurements, again coming from LHCb. So you ask them the question, how well is standard model doing in describing this? So there are very many measurements, very many variables. This is just a very small subset of them. And then you see at this last column that the standard model is in agreement with most of them. And if there are deviations, they are at the level of typically 2, at most to 3 standard deviations. Now, it means, of course, it's in the nature of experimentation that if you measure very many things, then it will happen that in some of these measurements, you will not hit the standard model on the dot. But the real question is, by how much is it deviating? And it's not more than 3 sigma, and that also only in a very few cases. Now, this is a quantitative way of describing all of this. So this is the chi-square distribution of electroweak penguins in B decays, which is obtained by fitting all the measurements that I was showing you. And so you see that the minimum of this chi-square is not exactly at the point where this delta real C9, that one of the Wilson coefficient, that would be 0. So it's not 0. Experimentally, it's determined to be -1 plus -0.25. So it's when you take into account all the uncertainties in the parameters, it's about a 3.5 sigma effect. So yes, standard model has been tested in rare B decays at the loop level in processes which are at the level of 10 to the minus 6. And it's found to be in agreement, and the largest disagreement is at the level of 3 sigma. Now, similar things have been measured in the case of B2 pi, L plus L minus. So let me skip all of this and show this measurement by the LHCb. So this is a process in which a B meson goes into a pi meson and L plus L minus. It is again a flavor changing neutral current process. Sorry, at the quark level, it is a transition of a B quark into a D quark. And why? Because the Kobayashi-Maskawa matrix element, Kabibo-Kobayashi-Maskawa matrix element, which enters in this process, is smaller. So this has a branching ratio of 10 to the minus 8. So this has been measured by LHCb, and this is the dilepton invariant mass, and these are the various calculations involving some of the lattice calculations, and also a calculation in which I was involved. And you can see that also in processes which are measured at 10 to the minus 8, the standard model is doing quite well. So, so this is once again, then at the end of the day, you ask the question, what does it mean in terms of these Wilson coefficients? So once again, it's this plot in which C9 and C10, the two Wilson coefficients are being plotted. If you can see the standard model point, so which is at 0, 0 in this new contribution. And the experimental measurements, these are 1 sigma and 2 sigma plots. You see it's about 2 sigma. The standard model is about 2 sigma from the standard model predictions. So I mean, it's another way to quantify and say that the standard model is doing quite well. Now, the last of this is Bs to mu plus mu minus, which has been measured, which involves different operators and different Feynman diagrams. And once again, if there are new particles, I mean supersymmetric particles, 2 doublet models, and so on, they can contribute to the loops, and they can change the branching ratio. So this has been measured now. Now, we are at the level of 10 to the minus 9. This is Bs to mu plus mu minus. And this is the measurement, which is a combined measurement of LHCb and the CMS collaboration. It has been well measured at about 6.2 sigma. And this is at the rate of 3 10 to the minus 9. The smallest of these involves B sub d to mu plus mu minus. It is at the level of 10 to the minus 10. It has not yet been completely measured. It's only a 3 sigma effect. Nevertheless, when you compare it with the standard model and ask how does it agree, it agrees with the standard model within 2 sigma. So this is once again the same game that you play in trying to find deviations from the standard model. The picture on the right side is a blow up of this region. And these are all the constraints coming from the rare processes that I have discussed. And you can see that, that the standard model is only about 2.5 sigma away. So this is, in other words, a statement that processes which are at the level of 10 to the minus 10, they have been measured. So they are 10 orders of magnitude, and the standard model explains these processes actually to within 2 or 3 sigma. So this is my summary. All of this lattice QCD, some rules, heavy quark symmetries, and all of that theoretical framework, which has been developed and is being developed further and further, which is the cutting edge of QCD technology. They've allowed us to calculate these processes very accurately. And in this particular case, which I talked about, BD case, they have been measured over 9 orders of magnitude, and they are found to be in agreement. The disagreement at the present time is at the level of about 3 sigma. Whether it indicates that we have to improve the QCD technology, or whether it is telling us that there is new physics just around the corner, remains to be seen. This is a program which is being pursued at the LHC experimentally, and it will be pursued at the KEK, the Super B factory, and we will see what comes out of this. So we look forward to this continued effort to study, test the standard model, and look for physics beyond the standard model through loop processes, through high luminosity experiments. Thank you.
Quick question. We have one here.
As you are well aware, there will be improved experimental data at Super B factory in the KEK very soon. But I'm a little bit more worried about the theoretical side mentioned here. In the case of gamma decay, the theoretical uncertainty is almost 5 to 10%.
Right.
And very quickly there will be much better experimental data. And even for this 2-lepton case, it's most of the decay has again 5 to 10% error in theoretical. And eventually we'll have a much better result from Super KK. So it will be very difficult unless there is a strong effort from the theoretical side. And what I'm worried about is the smaller and smaller number of theorists interested in this issue. And so you mentioned this the mu plus mu minus mode, which is 10 to the minus or 10 to the 10 branching ratio. It is the hardest part. And that's where probably we have least ambiguity in the QCD correction. But this is experimentally, it's a very difficult one. And I don't know how much KK Super B can do it. So I'm more worried about the theoretical side, and yes. I want your comment on this.
Yes, okay. No, thank you for this. You summarized it very well. The present theoretical accuracy in most of these processes is not better than 5 to 10%. And if the idea is that the experiments will reach an accuracy of 1% or even better, then of course theoretical accuracy has to be improved. Now, it will require a major effort. Now, something which can be done is to calculate the next order in perturbation theory. Now, it's easier said than done, because each order that you go in alpha S, the number of diagrams which increase is horrendous. But perhaps it can be done not in 1 year, but perhaps by a collective effort over several years. The hardest part lies in non-perturbative aspects. Now, these are coupling constants, hadronic coupling constants, form factors. Now, this will require a major effort. The only technology we know which can deliver us this precision is lattice QCD. And as you know, there is a very strong group lattice QCD in Japan, also in the US, also in Europe. Now, that requires actually a qualitative improvement. It not only requires, better machines, but better algorithms and better control about all the systematic discretization errors and so on. So this technology actually, the step in going from, let's say, 10% to 1% is a highly non-trivial step. And it will require a concerted effort over many years and advancement in the technology, in the calculational technology. And so we perhaps need new ideas how to calculate them. But this is definitely required. At the level of 1%, I think the present theoretical methods are not able to do, and there is every need to put in effort in that. Yes, thank you.
Thank you, speakers, again.